part.
There we go. Sorry, go ahead, Kaz. We're recording now.
Yeah. Many of you probably are very familiar with the topic, and this is a portion of our training that especially relates to OPC UA Information Modeling, which is possibly one of the most complex topics of OPC UA. However, we try to simplify as much as possible, especially in the context of the creation of information model as part of the publishing of the companion specification on top of a standard like MTConnect. We are assuming somewhat of an idea what OPC UA does in general. At the time of this presentation, of course, we were not targeting PubSub with the new transport, but the information modeling applies in general to OPC UA. I'm gonna go through some of these slides. Hopefully they'll be either clear enough or you can review it on your own later. And then I'm gonna show you a brief example on the practical aspects of information modeling and how that applies to the development of an OPC UA application. The slide and these slides are, kind of boilerplate from the foundations. So some of you might have seen it before. The specification of the OPC UA Unified Architecture. We are having some echo, so thank you. So there's now 14 parts to OPC UA. The parts that address information modeling are part 3 that describes the address space modeling, part 5 that specifically talks on how the information is modeled, what are the conventions and what are the aspects of abstraction of the information model. And then there's on the right side, you see the specification that relates to aspects of OPC UA relative to the application. And data access is the ability for an application to read, write, and subscribe to an object value and methods. Then alarms and condition programs and historical access for time series data or things of that nature. So there you go. The idea is that modeling, of course, the modeling is a way to provide information about what the system can do and what the device represents, what a software solution might offer to whoever connects. And it basically sits in top of the base services set of OPC UA as defined by part 4 and other parts, where the information modeling is agnostic towards what transport is being instantiated, whether you're using TCP, HTTP, PubSub, what have you. The specification are defined on top of the OPC access type information, and you might have a standard body like MTConnect that implements a specific information definition for their domain. And on top of the MTConnect, you might have a vendor that further enhances the data definition to fulfill the requirement of their specific products. If you make a robot with 12 axes for some reason, you might want to create your own 12-axis robot type on top of the MTConnect specification. And the layer on these allows the isolation of, the separation of concerns, so that whoever defines the information doesn't have to worry about the underlying plumbing of how the information is going to be carried across. The idea is of a unified object model, and by object is we mean that the object is an element that not only defines the data that is being exchanged, but also the behavior of the object, the business entity that the object is trying to describe. Therefore, you will have services that are specifically dedicated to the update of variables, process variables, tags, complex or simple. Methods, the ability to invoke functions from the client to the server remotely, and events, the ability of subscribing to an event from trigger on the server side by a callback mechanism, like any typical callback. All those aspects can be implemented in an object. And the reason why, of course, it's object-based is because it's designed to alleviate complexity. The requirement is to be able to describe an industrial automation entity in its complexity. And the complexity can be probably narrowed down to two basic object types in computer science terms. One is an array, which is a list of index value. One is a structure, which is a collection of elements that have a name. And so I mentioned that because, object-based and object-oriented programming are similar, not necessarily the same. The idea of complex type exchange existed before object orientation became popular. But it boils down to the fact that however complex the information you're trying to describe is, it has to be stripped down to its bytes in order to be streamed as efficiently as possible through the network among two agreeing partners applications. So this way you can see, well, the diagram is just kind of modeling a high-level concept where the data is exchanged among application in the form of objects and object properties. Oh, I just clicked on the slide, it didn't. There you go. And the principle is that the model has to carry both the information that you're trying to convey, but also its definition, so that a client application can discover what the server information is supposed to represent. So the metadata part is the part of the object that allows you to identify and qualify the object. Like you can basically infer the type definition of an object, its methods, its structure, and other concerns such its accessibility, the security aspect or the authorization aspect of the object. You see in the example here, there's an example of a PID controller. In this case, there's no method or events. There are the three classical properties, the process set and manipulated. Sorry, yeah, I had a blank. And that's just the type definition. Whereas this object specifically is an instance of the PID controller. So it's a very simple example of what that means. And both those information has to be carried through the wire among the two interoperating parties in order for the exchanges to be successful. So in OPC UA, we do not expect a client to be aware of the address space makeup of the server. That's actually common to other standards, as you might know, starting from the good old COM, CORBA, and so forth and so on. So that's the object-based representation. And the address space representation, which is a way to qualify an information model, includes both, so that you have the metadata and the application will instantiate specific object according to that type definition. This is probably classical computer science concept. How does OPC UA achieve that? Well, it does so by defining an elementary entity called a node. Everything in UA is a node. A data type is a node, and so is its instance. A reference is also a node, but we'll look at those. And you can see the hierarchy of the nodes, attribute nodes definition and their attributes in this diagram. You have a base node, so that at the minimum, your node should be identifiable by a node ID structure, which is basically a way to identify the node uniquely within a given address space. Then the node class, the browse name and display name differ in that the browse name is basically a human readable form of the node, what you would call a tag name probably, or name of the variable, whereas the display name is a localizable text that you can further define to help in the contextualization of specific locales for your entities. Starting from that node, you can specialize those nodes into objects, variables, methods, references, and other aspects. You know, the variable probably is the one that most resonates with the process folks. It's the process variable that has a value, has a data type. The data type is also defined by another node, and whether it's an array or not, and then the authorization part and other attributes that are relatively to the collection strategy for that variable. An object in general has one characteristic, one attribute, that is the ability of the object to allow clients to subscribe to events. Then you have a method. A method is specialized kind of a node that can execute a function. And of course, you will have input and output arguments and the likes. So you see the instance types on the top and the type definition nodes on the bottom. But as far as OPC UA is concerned, everything is a node and everything boils down to having a node ID. In the part 5, in the appendix, OPC UA also defines a notation. This is specifically relevant and specifically known to the folks that are editing the MTConnect companion specification. Whereas the UML notation is perfectly fine to describe an object-oriented structure, the OPC UA architects came up to come with an enhancement to that notation to further describe the specialized entity that pertain to OPC UA Information Modeling. And you see that those on the screen, and you can find those in the as a formalization, as a convention in the appendix of part 5, which is the information modeling specification, and for the OPC Foundation access types in the parts that deal with data access, alarms, history programs, and so forth. So the notation is pervasive. All approved companion specification will use them, and they just represent different shapes to represent different node types. Moreover, the connectors are so that there's no confusion between, you probably have stumbled on those before, composition versus aggregations versus information or tracing, in UML. Well, in UA, there is no confusion there. There's a connector type and the endpoint shape for every possible relationship that you can implement in an OPC UA information model. As a side note to whomever is going to work or is working on the component specification, you guys probably already have access to the Visio stencils that are provided to those working groups that deal with those. Last I know, we only have a Visio stencils. We don't have, for example, enterprise architects shapes yet. If somebody knows different, there will be a welcome announcement. So, as we saw in the previous slide with the basic hierarchy, at a minimum, those are the attributes of a node ID. The node ID, or the nodes, sorry. The node ID is a special way to identify a node uniquely within an address space. And there's some flexibility to it. It's not restricted to a GUID. It can be a numeric value, a string. It could be a URI, which are very popular in some of the standards that I deal with. As long as, and the structure specify which one is selected and uses and implements that. The base class of the node is indicated by the node class, so you know what is your basically what type is your node derived from. The browse name is the non-localizable readable text, so that the humans can make sense of that object. Display name is the localized version. And description is an optional localizable text that can further describe the entity you're trying to model. Here you see the node classes, which is the second attribute in the list that we saw before. So your base node, whatever node you make, your base node might be an object or its type, a variable its type, a data type, a method, a reference, and a view. We'll look at some of those, and you can see an example of that in that diagram, where you have these objects that are based off of a folder type, and the folder type has the one characteristic of implementing a reference called organizes, so it has the ability of grouping other objects, not unlike a folder in a file system, whereas a device might contain variables and properties. You know, you go all the way to a complex element like a PLC, which might have a couple of processors in the resources. You might run a program, so they're nested that way, and you can see that there's a base class on top, and its qualification in the name of the shape. We'll look at some of those in our examples. What is an object type? An object type, which is one of the node classes that you may choose, is the type definition of an object. You see here an example that uses the air conditioner. That's a very common example of some of the OPC UA demo. And the base object type in the OPC UA information models is, of course, base object type. And from that, you can derive your own. We have a controller type. And the controller type is a type that has these variables, a state and temperature, a set point, and other measurements that your controller might expose. Further along, you can specialize your own derived controller type into other subclasses. Well, there's an air conditioner controller, there's a furnace controller that inherit all the variables of the parents and enhance with their specific overrides. You know, you have probably seen these kind of strategies before if you dealt with any of the modern programming languages. So the OPC UA primitives and the stacks have all kind of services, in fact, as defined in part 4, for example. So all the APIs that are out there make available some of the functions that allow the system, a client system, for example, to discover the nodes and the relationship among them without previous knowledge of them by calling, for example, function that resolve that they can traverse this graph by calling a specific function. You know, there's a number of those, you know, and it makes the discovery mechanism pretty efficient. And when you implement your own standard like MTConnect that has implemented device type, then participant to the standard or application that adopt that information model definition can create instances of that without worrying about the conformity or conformance to the standard. The objects are the instance of the object types, and those are the typical items in address space. It's like at the minimum you would expect an object. Folders are special objects, as I said, that are designed to organize other objects, to group. So their main characteristic is to implement this specific reference verb. And the root folder, that's the always present folder, is the main entry point into any address space. Service server will implement the root folder. There is a boiler example, another ubiquitous example among the OPC UA demos. And you can see that this boiler has components and variables so that the relationship among objects are defined by one key reference type, which is the has type definition, and that defines the correlation between an object and its type definition, which is the object types of the previous slide. So, whoa, I clicked again and again. Variable type. Well, a variable type is specifically designed to convey the values that are changing in a server address space. So the base object type for variables is the base variable types for its type definition. And those variable types will have variables and properties. You know, we'll probably talk, well, there's always a question what's a variable, what a property is. Well, I would say by the book, a property is a variable that cannot contain other variables, so it's a leaf object. Probably a more conventional separation of those concepts is the fact that the variables is the representation of a value of a piece of data that will mutate throughout the life cycle of the application. You know, a process value, a temperature value, whereas a property might represent a characteristic of that object that does not mutate throughout the life cycle of the object itself. A unit of measure is a property. A high limit might be a property. You know, that's likely not to be changed. Doesn't mean that it can't. It could be changed at runtime, but it's just not. Definitely the fact that an element is the leaf of the tree is also characteristic of a property. Properties are not supposed to contain children. Well, cannot. Here you see some of that in the boiler example. You have the type definition at the bottom, and you have your boiler type that implements its own variables. In fact, the flow transmitter is probably the device that has a variable called flow measurement. The flow measurement is probably a float, and it's of type analog item type. It's a complex type. It's not just a number, but it also has a property that defines engineering units. And this diagram is following the convention. It might take some get used to, but if you're familiar with UML, you find yourself at home with this kind of convention. So the variable itself is the instantiation of a variable type. The variable, of course, can be typed in that it can be defined from any subclasses of that variable type. The slides repeats the concept where properties are the metadata of the nodes, the supporting information that qualify that entity, and they're always the leaf of a hierarchy. Here you see our flow transmitter with the flow measurement that has three properties: the ranges and the engineering units, or for example, the serial number of the device. That's the property. Whereas the flow measurement is a component. So there's a further qualification here of the reference type. One is a has property reference. One is has component reference. And references are one of the special sources of OPC UA, and those are not hard to explain. They're not easy to represent in a bidimensional tree. You might have seen this kind of modeling, you know. The reference provide a mechanism for an application to define a graph of nodes that goes in multiple dimensions. And it's the way of OPC UA information modeling to allow for a semantic representation of your address space. And the objects might have a clear relationship, you know, a hierarchical relationship. One is the parent of another, one is the container of another, one is its type definition. You see that some of those verbs in here. But you can also, well, the idea of creating a reference type, not just a set of possible relationships, but the ability of the user to define their own verbs to qualify a special relationship that two objects might have. It's extremely important in the implementation of generalized standards like MTConnect, IS-95, OpenSCS. So two objects might not just be in direct parent-child relationship per se, or class-object relationship. They also might have different reference types. The ones that are provided, so to speak, out of the box, you know, the primitive references are these ones that you can see, and they're separated in two sets. One are the hierarchical references, and one are the non-hierarchical references. The hierarchical references are the ones that you would expect when you see a diagram. One has a property, has a component, you know, has a subtype to it, organizes, so it's a grouper, like a folder type. Whereas a non-hierarchical reference is a relationship that an object might have to another that does not imply a parent-child relationship, generates event, has encoding, has a modeling rule, meaning that it's a mandatory, optional, so forth, has a type definition. So I'm going to click again. Methods. Methods are special nodes, and the methods that are represented with this convention, the ellipse. The methods might have input arguments and output arguments, and may have multiple output arguments. You know, and that's one of the privilege of OPC UA models. They can implement multiple outputs. Some of the object-oriented programming languages cannot. Some other popular ones like Python, Go, and you know, the new kids, they have this characteristic, and it's very interesting. The arguments can be complex types, and they are usually in standards. So the methods provides a way to allow a client to execute an action on the server side. Of course, the action can be sequenced it can be very complex in logic and can also have constraints. This, of course, provides a rather advanced way of implement some sort of RPC, but also in some of the most popular standards like PLC Open, PACML methods, and these kind of nodes are especially useful to actually model the programs as they are executed by a controller, an actual device control. Click. The data type node. The data type is, when you model your types, you will see an example. You can have basic data types, your integer, your floats, and so forth, but you can also have structures. And the structure is, there are some that come from the OPC UA specification and others that you might define yourself. And that allows you to describe a very complex data structure. So the data types is basically this big dictionary that describes those object definition. And data types can describe complex objects that are then used in variable types or in methods. Well, so what's the difference between a variable and a piece of data? Whereas a variable type defines a structure, an object that describes the properties and the variables and their properties that an instance of a variable would provide. The data type defines that very variable, the very value that the variable type might instantiate. So the data type is possibly one level of abstraction up from a variable. And the data type can be, an array, not just a scalar. It can be a structure, as we said, and it also can be used in a variable that can instantiate that through a data type ID, which is basically the null ID of the data type that the variable might use. The views is a particular aspect of information modeling that allows the address space to be represented as a given subset. And usually a server might implement views so that a client will see a different organization of the address space depending on, for example, who connects, who is the user that connects to it. And you would provide different views for different use of your server address space. And you have an example here. If the maintenance operator connects to that device, it might be interesting to see things that an engineer who designs the device is not interested. The views also are a way to hide informations that are not supposed to be seen. Of course, there are aspects of authentication and authorization of OPC UA address spaces that can also allow a server to hide information by simply elevating the access level for a specific user. Attributes. So you saw the hierarchy here, and you see some of the attributes of that. You can take another good look at it, but basically all nodes will have their attributes. Attributes are a specific set that are defined in the specification, and they have their own services. Attributes can be read and written too, so that a node can allow the call of the attribute service sets, read and write, to modify the information within the node itself. There was another slide here. The address space itself can also be exported and imported, of course. The reason to do that is because whereas the OPC UA Information Modeling, the way it's designed, it's it's designed to allow the client to discover the address space of the servers by just requesting. The ability to browse the address space itself, to gather the type definition and to reflect the types if so desired, and to understand what an instance is, how an instance is correlated to the other objects in the address space. But there's also the capability, and in that there is also specified in the OPC UA specification, of course. An address space can be exported, and at the current time can be exported as an XML structure that can be used, for example, by clients to become aware of the address space without necessarily connecting to a server and browsing it, but just by loading that XML file, which is called nodesat. In a similar manner, a UA server itself could import a nodesat in order to become immediately aware of the type definition for its own address space. And this is a classic scenario by which an MTConnect vendor might load the MTConnect information model in the form of a nodesat, which is a byproduct of the companion specification creation. They load up the nodesat, and all of a sudden they have the type definition according to MTConnect, so that they can create objects without fear of violating the compliance to the standard. So it's a rather efficient way to allow for the UA address space to be known, other than just connecting and browsing and those standard services. Modeling rules is an aspect of the UA model that defines the ability of a server to mandate the implementation of specific nodes and their attributes, whereas others might be optional to be compliant to that address space type definition. You also have two special rules, which are the placeholder. The placeholder is when you might want to reserve a place for a node. You just don't know what a node is yet. And why would you do that? Well, one example is because you might want to make sure that your very complex object has all the room available, and you want to be able to benchmark the overhead when it comes to network communication, for example. So you might say, well, I'm not done modeling this yet, but let me just put a few other nodes here because I know I'm going to need them. And those are also mandatory optional. Means that as a server, you must, if you instantiate an object, you must also instantiate its mandatory nodes, placeholder or otherwise. So the summary about type definitions in OPC UA: all types in UA are represented in the address space. All object types follow modeling rules and instance declarations, but their instance, they can basically create objects, and they can be an event notifiers. The variable types can have data types and can be carrying properties, or can be instantiating properties along with their variables values. Reference types are those specialized nodes that define the relationships among objects, can be hierarchical or non-hierarchical, and can be also created by the user. Once you have references, the browse services as defined by OPC UA specification and usually available in most of the stacks and SDK, reference types can be navigated, can be used in the browsing, in the querying. You can filter address spaces by reference and that allows you to basically model the semantic of your domain. Data types, of course, are those primitives that are important, for example, to identify or to qualify the value attribute of the variables. There, as other types in UA, they are extensibles and they are used to create your complex structures in your own information model. Information model standards, like some of that you've seen, but the specification themselves illustrates the definition of the types, of any types, object reference, variables, and so forth. You can create an information model standard to define standard methods, start, stops. Well, MTConnect probably will have a lot of those commands. Define properties, define the monitoring rules, what is required from a standard, what is optional for a standard, what is extensible for a standard. And then define the encoding for a data type. So OPC UA itself, of course, in its own models, like the one, the data access for alarms and so forth, already uses these mechanisms to create the, I would say, out-of-the-box set of service and behavior that come with the stack. And information, an OPC UA server may support different information model in one address space. This is very important. An OPC UA server might be implemented to conform to more than one standard. You might have a robot that uses a PLC that is developed by a vendor that model its controller using PLC open standard, but he wants to further define that specific application by implementing MT-Connect objects. So the standard will implement both information model, will import both that type of definition, and the address space has a mechanism to resolve that classification by namespacing, which is a strategy that is used in possibly all the object-oriented programming languages. You know, when you import something, when you do a using in .NET, you basically make your code participate to a specific namespace, and similarly, you can have your own information model. Think of it as packages or includes in your data definition. I quoted some of these information models already, and you recognize at least one of them. And information models can also be created out of others, like the PLC Open contains DI and not ADI necessarily, I don't know, but definitely DI. PackML is also an information model that contains PLC Open and DI models within itself. So it's also good, and the information models are published by the OPC Foundation, so they are definitely available for consultation and as a source of inspiration and ideas. So especially if you don't want to duplicate the efforts. I hit click again. The advantages of different things, of course. The typed object with variables, events, and methods. This is not just for OPC UA, but all these paradigms have the ability to, for an application, knowing the type definition, to also provide the tooling so that you can automate the configuration or the faceplate for the user interface, you know, for the creation of your applications. In second bullet point is specific to MTConnect and the exercise that you guys are going through of implementing a new OPC UA manifestation of your standard. And now that you're possibly more familiar with the conventions, it's clear to you where things can fit according to an OPC UA notification. And also, third bullet point is the ability to serve as some sort of a registry of your information, so that if anybody wants to know the makeup of your devices, they can just navigate the type definition of a server online by one system, and they will see how the address space is designed to work. And if you use views, of course, you can filter or reorganize subsets of information to satisfy different scenarios for different users. So before I get to the questions, I would like to show you an example on how that all takes place. I'm gonna escape from the dreadful PowerPoint, and I'm gonna show you an ugly picture. Some of you are familiar with this. But boy, this is a Visual Studio screen. I am a developer, and I am supposed to design a robot that has, I think, 3 axes. I actually didn't design this. Andrew did, my colleague, who's also listening. But when he designed that, he also created an information model to design its address space. The information model, according to the standards, can be designed by complying with an XML schema, so it can be represented this way. Well, this way it's rather hard for me to read. I'm a lazy programmer, so that's why I use Visual Studio. I want to use tools to do that, but nonetheless, the standards allow me to define all aspects of a node. You can recognize some of the terms you've seen in the slides, you know, display name, a node ID, which so happens to be an integer, a browse name for humans. Well, it's a stub that looks like a method, and all the stuff. I mean, instead of making that, I can go to this tool, which is available on GitHub. We developed a tool with the purpose of facilitating the effort of information modeling, but we use this also for training. There are other ways to create information models. This is one that you can use right away. It makes easier the life of a developer. It doesn't make OUA information modeling easy per se. You still have to know what you're doing. But in my case, I just want to open the model that Andrew made for me, the address space that he defined as a robot server. And I think I already opened it. It's a project robot server here. And I can see it's an object types. If I navigate, I can see that things are looking different. I have the types that are defined by the OPC UA standard itself. But I also have this robot type that kind of stands out. And I can see that Andrew defined these to contain a number of children. And those children are further qualified as properties and methods. So the properties, I see them here, they are simple types, you know, didn't do anything fancy. They're just 4 axes, in fact, not 3. And there are also tools. Because of we use this in training, and probably one enhancement to this robot type would be to make an MTConnect robot type and make it comply with the MTConnect standard. This is a simpler version of it. Does not implement MTConnect. Just shows the value of the axes and allows me to stop the robot, to increase the speed, to set it automatic or manual, and then also as the classical training method which you can instantiate, you can implement a multiplication by inputting the two factors and outputting the result. So if I were to create this an instance of this robot, because I do want to implement a robot, I have a small robot, I want to use this information model to expose those axes. I go right here and implement a robot 1. As I instantiate that, all its axes and methods are available. And then as a developer, I just compile these. And the word compile means for the purposes that I'm going for, it has the effect of translating the model XML into the OPC UA compliant node set XML, which is the standard XML file that servers and clients can import if they are conformant to the specification. And so I did. I actually created that node set, and now my code can instantiate that. What does it do that? Well, it does it in source. In this specification, I'm not going to go through that level of details here. My robot server here is written using the Matricon SDK. It's one of the possible SDK, and I chose C++ to write it. So that if I build and run this server example, which is compiled as a console app, I should be able to see how my robot behaves. But more than anything, whatever this thing does, one thing for sure I'll be able to retrieve, and it's its address space definition. It did implement my robot server information model. So if I connect with the generic client tool like UA Expert, and not bothering you with the connection, I already had it set up. Any server, besides having a root folder, as we said, also has types definition, and wherever implemented views, I didn't implement any view, nor did Andrew. But I have the types, and you can see here that you see all the categories of type that I can see. So even if I didn't know the node set, I can go here and see, well, what kind of nodes I have. Well, somebody already expanded that. And because I know all the OPC UA types by heart, this one, I never saw it, so it must be something different. It's robot type. But another piece of information tells me that this is something that somebody else did. If I go to, I don't know, message reader type, don't care what it is, but one thing I noticed is of namespace index 0. That's a telltale of the fact that this is an OPC UA type, meaning that it comes with any OPC UA server, is defined in the OPC UA specification, is a, so to speak, primitive type. Namespace index 0 is reserved by the OPC Foundation. Anything else that you might create in MTConnect or I might create as a robot will use another number. So the fact that robot type is not of namespace index 0 tells me that this object type definition is made by somebody. So it's likely. So if I wrote a client code that can navigate, the one thing I could filter out is like, well, give me all the name, all the type definition that namespace greater than 0, for example. So I can see that I have a robot type, I have an axis. I can see that what that axis is, the data type. I can see the multiply method. I can see the stop method. The stop method doesn't show much interesting things, whereas the multiply has inputs and outputs. So that might be a little bit more fun to play with. But further along, I can also say, not in this client, but in the client code, I could say, well, okay, give me all the instances of robot type, probably placing the object. And I can see that there's an immediate instance under the object folder. of my robot. And if I make a subscription here, of course, I can see the things running. So as I call, I can see the values of my methods, and if I call the methods, I get possibly a good result. But the main part that I want to convey here is the ability of a client to discover the type definitions by a standard service call and navigate to the specific type. You can see that every time I do something here in US, but there's a message in the log, and the message is basically telling what is the service among all the OPC UA service sets methods that I can use. What is the one that has been called by this client action? And browse is the one service that is used to navigate an address space. So you browse, and of course read is the function that is immediately called right after that to populate this pane on the right side to further display the attributes of the specific node, which is a type definition. So that's the one thing about information modeling that is extremely powerful, so that the client can, and there are other services that allow a client to, even if the server allows, to dynamically create instances and runtime and so forth, and interact with the namespace. Loading an XML file is just one way of interacting with an OPC UA server namespace. Before you ask, this is the UA Model Accelerator. In case you're interested in that, there's a Beyond website or the project on GitHub. If you don't want to compile it, you can go to the website and download the free tool to play with some of those models. Why do I show you that? Because I'm going to show you in a minute. There's a lot of OPC Foundation and MTConnect material on GitHub. So here you'll be provided with a link as part of this, as a follow-up to this conversation. But you can download the tool and then go back to your GitHub. And on GitHub, you can also find some of the approved node set from the foundation in the UA node set project. In the UA node set project, beside the actual implementation of the schema in compliance with the requirement for the import and export of information models, you see that there's a number of information models that are implemented following some of the popular standards. Lo and behold, there's an MTConnect node set, and you can see that you can already have the model. When you install UMX, the UMX itself comes with those node set preloaded in its examples folder, so that if you go, I'm currently navigating to it. If you go to the program files, you're probably not seeing me navigating for privacy reason, but I'm gonna get there in a second. I think it's program file x86. There you go. Beyond UMX samples. Under samples, you can see a number of information models that are created as part of the component specification release. The one that you're familiar with, and I believe that this probably Randy Armstrong is actually on the call and can confirm which version of the specification this is. Probably not the latest, but here you can see the MTConnect information model. And there are these, the device type, asset type, and cutting tool type, that if you go to the actual component specification, I have a release candidate, so this is probably not coherent with the actual model here, but you have device type and component type. So you can use these to make acquaintance with the actual manifestation of the information model. And if you're keen to write some code, you can generate a node set and pick an SDK and create your own little robot and play with it. But this is probably one of the best ways to get used to the OPC UA development.
Cause, can I interject here?
Please, Randy.
Yeah, I just wanted to explain the tools. There's the node set is the interoperable format. That's what the specification defines. And so that allows tools like the one that Cause develops to operate and load it. However, the existing master for MTConnect is actually in a file format that is handled by the command line tool called the model compiler. So what we do as part of the UA specification work is we don't use the graphical compilers. We use a hand-edited XML file, which is an input to the model compiler, and the model compiler will generate the node set. So it's like an XML to XML converter, so to speak. Now,
I should clarify that. That's what the UMX.
Yeah. Sorry, go ahead, Ghost.
That's exactly. I should have said that there are two main. One is the model compiler that takes a model design input and creates a node set, and that's exactly what the UMX tool does. It just manipulates that model design file so that.
You are editing the model design file. Okay, yes, that's great.
That's why I'm glad that you made that comment, because there's no magic in the UMX. It's a simple tool that just makes your XML typing a little bit easier, and it makes it easier to present an information modeling training or specification work. Okay. But it's important. Okay. We call it compile, but it's XML to XML transformation.
Okay, that's good to know, because it means we don't have to make a decision which format we're going to do this in.
Correct.
At the beginning.
That's what we did it on purpose. Yeah, exactly. I should have explained that before showing the compile the UMX. That's a good point.
Okay.
So yes, of course there are different ways to skin a cat, but as Randy said, as we make companion specification, we have to make sure that we comply with the general specification. So using the version of the model compiler that supports a given OPC specification guarantees the fact that the node set is going to be generated by the model compiler, which is conveniently invoked by the UMX if you so choose, but you can also edit the model design by hand. That will guarantee the fact that you will have a UA compliant node set that can be then loaded and discovered. All right, so I think I'm back to my questions and answer slides, and I'll take a few questions.
That was very helpful. Thank you.
Sure, and also beside the fact that we are in the same group, so we can communicate. Otherwise, you will probably be able to see the recording here and send the questions as you go through the investigation of your own journey through UA. You know, we take those offline if needed.
It seems like a pretty straightforward object modeling process. You know, very similar to a lot of the other object modeling.
Correct.
And UML type semantics that I've played around with in my many years. So yeah, no, it looked good, and I think that clarified some of the sort of base assumptions. I'm just looking through the MTConnect model right now, and it's made me think now. There's just some artifacts that you talked about, which I think we can definitely clean up, probably because when we first did this, we're quite as clear on some of the references and the way use of references within MTConnect versus some of the artifacts like, you know, components and data items and so forth, which I think can actually be remodeled and maybe cleaned up a little bit to make it more compliant with the way that you think about the structuring of data. So some of those, like if you think about the edges, UML edge between or connection between two things, we have aggregations, you have an aggregate or components or such that may map better to some of our semantic model, which may not have been clear when we were first reading through it and trying to do the relationships.
Right, and as I think the discussion was at the beginning of this call, as you go through the newest aspect of OPC UA that also has information modeling implication, that might be worth considering for MTConnect. But in your case, you also have the privilege of having Randy Armstrong, Paul Hunker, Andrew Cullen among the MTConnect members. So I'm sure that you won't have a problem figuring this out, so.
Yeah, a lot of new things to think about. I mean, Randy did a great job, and originally, but I think just going through this with a new set of eyes also, and kind of reevaluating, so it would be a great exercise.
Oh yeah, absolutely. The one
You
thing
also have to remember that there's been a certain amount of learning going on within the OPC UA working group itself. We've sort of realized that our own way of looking at things originally wasn't ideal, and we sort of evolved our own thinking over time. So that's
definitely.
it's kind of a two-way thing here.
Oh, definitely. Yeah, no, that's how I meant is that everything is evolved, and we're both. You guys have probably done 1,000 of these things now, whereas I think when we were first doing it, we were kind of new at all of this stuff. So definitely a good opportunity to redo this and clean it up a bit, and and I'm looking forward to it. But this is really helpful in understanding the modeling techniques that you have and how things are put together.
Sure, and I'll be looking forward some sample code. There's a lot of sample code on MTConnect on GitHub. It'd be nice to see an OPC UA reference implementation in it, so that we can start playing with, there isn't.
So I talked to somebody yesterday who has an intern who I think is going to be working on exactly that. I can't, give him more information 100%. Until I have it 100% locked down, but it will definitely be open.
Yeah, that'd be good. If at least to the members of MTConnect, that would be a very useful tool.
Yeah, it'll be open to everybody. So to the everybody. So, but this is going to be hopefully a summer project, and once I meet with them and just make sure that everything is okay, I can probably, the group that's doing it is open group anyway. So it's just before I give out names.
Sure.
Get them in trouble. But anyway, we should be able to socialize that probably within a week or so.
Excellent. Yeah. It usually speeds up the awareness.
All right. Can I? I'm sorry to interrupt. This is Martin Knopps from Harding. Just a question from let's say non-expert. This is obviously very, very, very high level material that is presented, which is very impressive. But again, I'm one of those observers, as you have also other people that are doing that. And again, one general question, if possible, I could ask at this point is the following. Last week, I think it was you, William, that really presented MTConnect, not only based on the architecture, but also based on the content. So my question at this point, after we have seen the presentation of MTConnect and OPC UA, a simple question I have is on the parties involved with this companion code discussion, let's say any intention or any interest or any basis for any discussions on the content that basically is currently in MTConnect, and again, based on initiatives currently undergoing in Europe for the content of, let's say, an OPC UA initiatives for machine tools that may or may not include other contents that MTConnect has so far. I mean, is that discussion at all part of this companion code discussion, or is this something that I really should take on somewhere else?
Are you talking about the machine tool companion spec work that's been done in Europe already?
No. I'm talking about the MTConnect presentation last week. Clearly, beside the architecture and the method of communication, also described in detail all the, let's say, all the parameters, all the basically the information that was agreed to basically define that can be taken out of a machine, whatever 190 parameters. So the presentation today on OPC UA, obviously OPC UA is a format of communication, but it does not in itself define what information comes out of the machine tool. That's completely up to the user. So I'm only asking to understand the intention of this discussion going on right now for this companion code, whether at this point we simply assume that whatever is in MTConnect as those current parameters that are defined is going to stay the way it is, and the companion code will basically enable to get that content out of the machine, but then convert it over to OPC UA code.
Yes. Yeah. I think the answer to your question is absolutely yes. I mean, that's the whole purpose of creating companion specs on top of OPC UA. As you understood from today's presentation, OPC UA you can create any kind of information model you choose, but the reason for the MTConnect or any of the companion specs is to have standard information models that can be used in specific industries and specific purposes, so that not everybody out there is reinventing the wheel and creating variants. We have more, standardization. That's what the companion specs bring. Does that make sense?
It makes sense. Again, my question is just beyond that. My question is basically, since we went into the details last week about the content of MTConnect, I guess that was just for information purpose and not to, let's say, with this current initiative that we are doing now for the companion spec, there will be no discussions about expanding the parameters in the machine, adding more possible sensors, since the smart machine discussions are very fast ongoing right now. So this discussion right now for this purpose of this companion spec revision will have no intention to discuss about the content itself, just the method of how to do it. Is that correct?
This discussion, yeah, but I think what you're talking about is can we extend the MTConnect model to include some of the new smart manufacturing or smart machine capabilities that are being discussed, like within the Industry 4.0. Sure. If that's the question you're asking, I would love to have people from that group contribute to MTConnect, and by sort of association with this group, those changes will make themselves apparent in OPC UA, almost immediately as we rev the MTConnect standard. The OPC UA MTConnect companion spec will also be revved in parallel. But yeah, we'd love to have that information in MTConnect. If that answers your question.
Okay, thank you.
Yeah, I mean, just to be clear, I think that is a separate discussion, and as Will said, that's a discussion that the MTConnect group would love to have and add that to that standard. And if it happens coincidentally at the time that we're also working on this companion spec, it'll flow right into the companion spec with OPC UA. But it's a separate discussion with a separate dedicated MTConnect group.
Okay, thank you.
There may be some overlap in the VDW OPC companion spec, but I'm not exactly sure of the details of that.
Hmm.
And I was going to add that we have within MTConnect a number of working groups working on different segments of manufacturing equipment, and particularly the machine tool working group. And that probably would be a good initial interface between the, any requirements or new information that comes from Hardings themselves or from other companies or organizations to link into the MTConnect development process. Be through the machine tool working group.
The other thing is, I think as we rev the standard, I mean, I see this as the companion spec process as an ongoing effort. It's not going to be sort of just a single point in time. We've done it. We're done forever. Because MTConnect is evolving. We're adding new things to it. We're adding new models. So the objective is to keep updating the companion spec as MTConnect evolves and adds more information. There's a lot of work going on, as John just said, in many different areas. So we'd like to keep this as sort of an ongoing, continuous process. And I think once we have the foundation done within this companion spec, then the additions will be pretty simple to add in there. Because we already have the framework.
Mm-hmm. Okay. Any other questions? So, as I said in the beginning of the meeting, we'll schedule a next meeting probably 2 weeks from today for the larger group, and probably move it to the time that we originally agreed as the regular meeting time at 2 p.m. I think, yeah, 2 p.m. Eastern time, starting in 2 weeks. And in the meantime, Tom and I and others are going to be kind of getting together in smaller meetings and discussing our path forward and how we're going to actually get this thing done. You all have, and I can, in the meeting minutes from this meeting, I'll share again the people that have signed up for various roles. If you want to be actively involved, please let us know. We're certainly open to involving more people to help get the work done. So let us know, and we're happy to include others. But that's the plan. We want to start working and getting the people together that are going to get the work done. All right. If there's nothing else, then I think that's it for today. Thank you, Kaz, for the presentation. Tom passed along his thanks as well. He thought it was very, very good.
Thank you.
Tom had to leave early, so yes, thank you. All right, everyone. Thank you. Have a good weekend.
Thank you, and thanks so much for the presentation. This was super helpful.
Thanks, guys. Have a great weekend.
Thank you, guys.
You too.